Hey everyone, welcome back. Hope you had a good weekend. Get some notes here on 29-3. You can find this in your book on page 453. Just a reminder, as before we get started, I'll be having an office hour today, every Bronco day, and today from 10 to 11 a.m. So stop in if you can, ask a few questions, just say hi, do whatever you need to do. So here we go. We got some things for the word wall. Obviously, we don't really have a physical word wall unless you're still keeping notes on the one you had. If you are, that's great, but check it out. Today we're going to talk about some discontinuity. We actually talked about that already, but we're just giving it a vocab word. Discontinuity is a break in a rational function graph that happens for values of x that cause the function to be undefined. So we saw that last week when we were finding the vertical asymptotes, right? Those are an example of discontinuity. The reason we're giving that a more specific definition is because today we're going to look at another type of discontinuity called removable points of discontinuity. So the hint there are points, and another name for these are holes. So you'll see on the graph here what we're going to do, instead of having an asymptote, we're going to have an actual hole. You know, graphs are made up of points, right? Infinite points. We got points, points, points all along the graph. And what we're going to say today is one of those x values is not allowed to happen. And we signify that on the graph by literally putting a hole there. It's almost like a pothole that you'd have to step over. And as you're connecting these points, you'd have an infinite amount of points on this. This is just a line here. But you'd have that one x value that is an open hole. And that is a removable point of discontinuity. So, and that's what we're going to see on our graphs today. When this occurs is when you have common factors in the numerator and denominator that reduce to 1. Okay, so I'll show you in a few examples how that looks and how you know when you have a hole. One quick note here is that at 1x value, a rational function cannot have a hole and a vertical asymptote. It can only have one or another. So a mistake I see a lot is when you have a hole or something, some students try to do a vertical asymptote like that as well, and that's impossible. That won't happen. You can either have a hole or vertical asymptote at an x value. You won't have both. All right, so check this out. At the end, we're going to piece this together and sketch a few graphs, but let's just start by identifying the vertical asymptotes and any holes. Okay, so the first step, just like the graphs we did earlier or late last week, is we're going to factor everything. Top, bottoms, whatever you see that's factorable, go ahead and do it. So the bottom factor is x plus 2, x plus 3. Okay, so what you can see here is we have something that reduces. Now, like I said last week, or we're going to start to see this week, I didn't say it last week, but what you're going to start to see this week is when something like that reduces, you kind of get a new function here. Now, later on when we start graphing and stuff, we're actually going to use this reduced function more than we'll use the top one, but that would be more important later on. Right now, it's just asking us to know the vertical asymptotes and the holes. So this guy here, right, we're going to treat this just like we did last week. This guy does have a vertical asymptote, and that happens at x equals -3. So that procedure has not changed, okay? Here's what's new, though. When this x plus 2 term cancels or reduces to 1, top and bottom, the whole of this graph is going to happen at an x value of 2. I'm sorry, I misspoke. -2. Let me fix that. -2. All right? So here's what you got to think through. -2. Just like the asymptote, the vertical asymptote. We take that x plus 3. We think through, we set x plus 3 equals 0, and that's what gives us the -3. Just like we found our zeros, just how we find our x-intercepts, right? If the x plus 2 is the term we care about, imagine setting that equal to 0, and the x value you care about is -2. Okay? So that's the first trick, is if x plus 2 reduces, the x value of the whole is -2. And remember, the hole is just a point. Instead of a solid point, it's an open point. So now we have to find the y value. Well, you know how to do this. To find a y value, remember this is an x value. If you want to find the y value, you plug it in. Here's the key. You want to go plug it in to the x value of -2 into the reduced form of your function. the function that happens after everything is reduced. Okay, so if I plug -2 into that bottom function, all right, the one I boxed in red, I'm going to get -4 up top, and I'm going to get +1 down low, so that's just -4. All right, so holes, like I said, they are points. They're going to have an XY value. Okay, so if you're going to find the X value by something reducing in the top and the bottom, reducing to 1, and you're going to find the Y value by taking that X value and plugging it into your reduced function. Let me just check that whole -4 up top, +1 down low. Yep, the hole is at -2, -4. All right, so that's how a hole works. Let's try a few here. So pause the video, take a second, and reduce top and bottom as much as you can, and see if you can identify the vertical asymptotes in the holes. Okay, so let's see what you did. Up top, should have factored the X out, and we'd have an X over X minus 1. On the bottom, this factors to X minus X plus 4 and X minus 1. All right, so right away, I can see there's a hole. X minus 1 is going to reduce. I'll come back and finish up that hole in a second. So my new function here is going to be X over X plus 4. Okay, I'm just going to box that because I want to remember that's what I'm using here on out. I can get my vertical asymptote from there. From the denominator, it's X equals -4. Okay, now my hole, because X minus 1 was the term that canceled out, the X value of the hole is 1. To find the Y value, I take 1 and I plug it in to what I'm boxing right here, right? I plug it into my reduced function. So if I plug in 1 there, I get 1 over 5, so 1/5. Sometimes these holes will have ugly Y values. There's just no way around it. But you'll see in a second we start graphing, the nice thing is that is a point. We're going to use that point to graph. Go back to my little example here. You have solid point, solid point, solid point. The hole is in line with all those other points. So you can use that when you're sketching your graph to help you figure out what's going on. Okay, let's do the other one here really quickly. If I reduce, factor everything, let's see what happens. The top is already factored. Down low, I can factor the 3 minus x, 3 plus x. That's an a squared minus b squared. And then the 3 minus x is reduce. So my new simplified function is just 1. Be careful, it's a 1 up top, not a 0, over 3 plus x. You could write that as x plus 3 if you want. It's the same thing. So my vertical asymptote is at x equals -3. And my hole, because 3 minus x reduced, now again, you can always go over the margin here and do some work. If you set 3 minus x equal to 0, right? Easiest thing probably is to add x to both sides, and you get x equals 3. That is the x value of your hole, okay? So the x value is 3. To find the y value of the hole, plug it in to the reduced function here that I'm boxing in red. If I plug in 3 there, I get 1 over 6, so that's the hole. Again, sometimes holes have ugly y values, but that's how you handle them. Okay, so we've done vertical asymptotes, we've done holes. Holes are the new thing today, the removable points of discontinuity. The last thing we need to talk about really quickly are vertical asymptotes. Okay, so if you're in class, we would talk here a little bit with your teammates. In the last lesson, we found these horizontal asymptotes by using transformations. Everything was written with a d out back. I can move it up 2 or down 1, etc. But if you look back at these last two examples, right, they're written as one big fraction and one big fraction. One big polynomial divided by a polynomial. So the transformations aren't very helpful at all. So we have to just know a pattern, right? Now, if we graphed 100 of these rational functions, we would see these patterns develop. So it's just something you got to know. It is on, these 3 options are on page 454 of your book. So it's nothing you have to write down. Maybe just earmark that page so you can go back and look at it later. There's 3 different things, 3 different situations you got to look at. They're going to tell us the different types of horizontal asymptotes we're looking at. Now, this is only if it's one big fraction, right? 2 polynomials, one up top, one down low. If it's in that form last week where there's a transformation, you can just go up 4, down 2, or whatever. All right, Option 1, when the degrees are the same, top and bottom. So you have like an x squared over x squared, or an x to the first over x to the first. The horizontal asymptote is the ratio of the leading coefficients, right? So whatever number is out front, you divide those, and that's going to be your horizontal asymptote. I'll show you an example of that in a second. All right. Option 2, when the denominator degree is larger than the bottom, the horizontal asymptote is just 0. That's a nice situation. That's really easy. When the bottom degree is higher than the top degree, then it's automatically y equals 0. That's it. Now, there is a third case when the numerator degree is larger. So when you see something like x cubed over x squared, there is no horizontal asymptote. There are other types of asymptotes, but those are beyond our class. You'll learn about those in pre-calculus. Okay? So right now you're looking, if the degrees are the same, you take the leading coefficients and you divide them. If the denominator degree is larger, it's just 0. And remember, all horizontal asymptotes are y equals. They're horizontal lines. So we have to have that y equals out front. You can't just put a number that doesn't tell me anything. Okay, so let's practice a few. Let's just try to decide what the horizontal asymptote is. These are pretty quick hitters, but we'll just rewrite this first one so you can see it. It is better to put these in standard form. So you want the x's out front in descending or descending degree. So you can see in this first example, I have x to the first up top, and I have x squared in the denominator. So the degree of the denominator is 2. The degree of the numerator is 1. This first one is case 2. The denominator has a larger degree. So if I see that, immediately the horizontal asymptote is y equals 0. You really don't need to even show any work. It's just you have to know that case, you have to know that situation. All right? Option or example B, letter B, well, actually, there's nothing even to rearrange. Well, I guess I could do this. Let's factor out 2 here, x plus 1 over x minus 1. Now, that's going to be a good first step. I would do that just to make sure I don't have a hole. Nothing reduces here. So it's really kind of pointless to do that. You could keep it factored, the 2 factored out if you want, or you can just go look at what you have here at the very start. So what we have is we have an x to the first up top and an x to the first down low. The degree of the numerator and the denominator are the same. So when they're the same, the horizontal asymptote is the ratio of the leading coefficients. So the leading coefficients are the numbers out in front of the lead term, right? So the leading term. So there's a 2. When you don't see a number out in front of a variable, we know that's a 1. So those are my leading coefficients. So the horizontal asymptote for this example is y equals, remember always y equals, 2 divided by 1, which is just 2. All right, simple as that, finding horizontal asymptotes, okay? Pause the video and go through these 3 really quickly. Just make sure you can find and identify the horizontal asymptote for each one. All right, so for A, I'm just going to rewrite these in standard form each time so you can see it a little bit easier. That's what that should look like. For B, there's really nothing you can do, and for C, there's nothing you can do. I mean, there's some factoring here, but we're just finding the horizontal asymptote, so everything's in the right spot now. Here's what we got. X to the first up top, x to the first down low. Same degree top and bottom. So the horizontal asymptote is the ratio of the leading coefficients. All right, so these leading coefficients, this is a -1 up top. This is a +1 down low. So -1 divided by +1 is -1. There's your horizontal asymptote. Done. Okay. Option B. Top degree is bigger than the bottom degree. Let's go back to our list here. The numerator degree is larger. That is the one we're not looking at right now. So if you see something like that, you can say no horizontal asymptote. All right. And be done. This problem is just, these problems are just asking for the horizontal asymptote, so if it doesn't exist, you just can put that doesn't have one. We're not going to graph many that don't have a horizontal asymptote, but you should be able to identify the ones that don't have one. Letter C, you got an x to the first up top, you got an x squared down low. The top is smaller than the bottom is bigger than the top, so the horizontal asymptote is automatically y equals 0. So again, not much work to be shown for the horizontal asymptotes. You just need to know these three rules on page 454. All right. So let's piece them all together now. All right. I got two examples here where we're going to graph everything start to finish. Pretty good example of what kind of problems you're going to see on the fluency test, how you're going to have to be able to wrap everything up and summarize everything. Okay? So this is in your book. This is example C. Just find the next page in your book. I'm not sure what page, but find it, example C, and we'll start it together. So the first thing you got to do is factor everything out. Okay, so we got an x squared plus 5x minus 14 up top. That factors to x plus 7, x minus 2. On the bottom, you got an x plus 2, x minus 2. All right, so we do get something to reduce here. The x minus 2 is reduced. That means I'm going to have a whole. Let's rewrite this final thing here as x plus 7 over x plus 2. All right. Now, remember, I'm putting a rectangle around that x plus 7 or x plus 2 because when I do all of this stuff over here, and when I graph it over here, I'm going to use this x plus 7 over x plus 2. You can always use the simplified version. The only thing you have to remember is that you're going to have a whole. So I like to take care of that first. X minus 2 is reduced. That means my whole is going to be at 2. Excuse me. Now, to find the y value of that whole, right, I'm making a table. You're going to make a table for a few points here. Might as well start it for the whole. All right, so the whole is at 2. To find the y value, I plug it in f of x, and plug it in right here. So if I plug in 2 there, I get 9 up top, I get 4 down low, so my whole is at 9/4. And I'm just going to write next to the table so I remember that that's a whole. Okay? If you're having a hard time, if you find that you miss or you forget to graph the whole with an open circle, I'd say go ahead right now, go to 2, and then 9/4 is a little bit over 2, right? 2 1/4. So 2, 9/4, and I would just put an open hole right there at around 2 1/4, just so when you go graph it, you remember that that's an open point, not a solid point. All right? Okay, now the rest is pretty much the same. Again, looking at this reduced function, vertical asymptote is x equals -2. X-intercept, you can try this on the margin if you want, plug in 0 for y. You're going to get an x-intercept at -7. Okay, -7, 0, that should say. All right, plugged in 0 for y. Y-intercept, plug in 0 for x. By the way, I put an S there for x-intercepts because you can have more than one. Right? Some of these graphs will have more than one x-intercept. Y-intercepts, though, you only have one. These are still functions, so all functions have to pass the vertical line test. You can't have more than one y-intercept. And you don't have to have a y-intercept. Think about if the vertical asymptote was on the y-axis, you wouldn't have any. So a lot of them do, though. If I plug in 0 for x here, I get 7/2. All right? Now the horizontal asymptote, if I'm looking at my reduced function here, the horizontal asymptote, you can actually look back up at the original 2. So you could have done this from the beginning, but I'm going to do it here. X to the first over x to the first, same degree, top and bottom. So my horizontal asymptote is the ratio of the leading coefficients. Those both of those x's have a 1 out front, so it's just y equals 1. Okay, so I've got pretty much everything I need. Almost everything. You'll see in a second. I'm probably going to need to add a few more points to this table. And the domain and range I recommend doing at the end. It's going to be a lot easier at the end looking at the graph to finish the domain and range. Okay, so that was some water. Stay hydrated, guys. Keep drinking. So let's go over here and start graphing this, okay? We got x equals -2 as my vertical asymptote. Right there. We got y equals 1 as the horizontal asymptote. Right there. All right. We got an x-intercept at -7. I like the way this is working out. It kind of looks like things are in the right spot. A y-intercept at 0, 7 halves. So 0 and 7/2, 3.5, 2, 3.5, right there. And that's everything. My horizontal asymptote is y equals 1. All right. So if I look at the graph right now, I don't even really need to add more points. I've got a solid point up there and a hole in the top right quadrant of this graph. So I know that this piece up here, this branch, is looking something like this, right? Remember, these graphs always approach the asymptotes. Now again, when you get to that hole, the hole is just like when we do interval notation, it's an open point. So I can get as close to that hole coming from the left, and get as close to the hole coming from the right, but I can't hit the hole. This is like a pothole in the road, but it's still on the graph. It's a point in line with all the other ones. You just have to skip over it, and that's why we put an open circle. All right, now the second branch, I'm pretty sure it's going to be down here. But might be a good idea to check. If I come back over here, the vertical asymptote is at -2. So I don't know, let's just plug in -3 just to make sure we like what's going on. If I plug in -3 up top in the function f of x, I get 4. If I plug in -3 down low, I get 2. So, no, I'm sorry. If I plug in -3 down low, I get -1. So that's going to be -4, right? +4 up top, -1 down low, -4. So -3, -4 is down there. And I feel good now about my second branch being in that bottom left-hand corner. So make sure you're approaching your asymptotes. In the homework you guys did, these graphs looked pretty good. So make sure they're nice and smooth. No sharp turns or anything like that. Arrows on the end, but never crossing the asymptote. All right. There's our first example. Notice that red hole. Let's go back and do domain and range. Now there's a little trick here. We have 2 places that have discontinuity, right? We have the vertical asymptote and we have the removable point of discontinuity. So we have to have both of those in our domain and range, okay? So the domain, look in the graph, it goes -infinity all the way up, moving left to right to that vertical asymptote at -2. Then union goes from -2 to my hole at +2, right? So -2 to +2. And then union, after the hole, it goes to the right forever. So to infinity. Oops. Let me move my table over a little bit here, because it's in the way. That. All right. So, and then the last piece is to infinity. So that's my domain. Now range, same thing, going bottom to top. This goes down forever. So -infinity. It's rising up all the way to the horizontal asymptote at 1. Union. Now here's where it gets a little tricky. After 1, so you have all these points in between the horizontal asymptote and your hole, but you have to skip over the hole. So you have to go from 1 to the y value of that hole, which is 9/4. That's why it was so important to up top to find that y value, not only to graph it, but to identify our range. And then after 9/4, it can go on forever up to infinity. And there is our domain to range. Again, easiest way to do domain to range is at the end. After everything's pieced together, just look at the graph. Domain left to right, range bottom to top, focusing on interval notation. All right, there's the graph if you need to see anything else on it. Okay, let's do one more. So this is on page 456. I'm gonna give you a minute. You can pause the video here. I'm asking for all the same stuff. And here's a graph to try it on. So take a second and see what you can do. All right, let's do it. So if I factor everything out, I have an x minus 2, x plus 2 up top. On the bottom, there's a GCF. Let's see if we can save a step here. Let's go ahead and take the GCF out right away. If I take an x out, that's an x squared minus 3x minus 10, right? Save me so I don't have to rewrite the whole thing. So now that inside the parentheses is factorable, to x minus 5 and x plus 2. Now these first two examples both have a hole. Not every problem on the homework tonight will have a hole. I just wanted you to see two of them. So that reduces. Hole is going to be at -2. We'll find the y value here in a second. So my reduced function is x minus 2 over x times x minus 5. Again, that is my reduced function. That's what I'm using. To find the y value of the whole, I plug -2 in to this reduced function. So if I plug -2 in there, let's see what I get. I get -4 up top. I'm going to write this out. On the bottom, I get -2 up front, and then times -7. Right, so there's a lot going on there. So I get -4 over positive 14. Like I told you, these y values get ugly sometimes. That reduces to -2 over 7. Let's double check that and just make sure nothing's wrong. Plugged in -2, got -4, and then -2 times -7 is 14, and that reduces. Yep, I think that's good. So there is my hole. Again, if you're worried about forgetting to put an open circle, you can go graph it right now. I will wait until we change pages. All right, vertical asymptotes. Now this is unique. I've got two here. I've got one at x equals 0 and another at x equals 5. It's okay. You might see that happen sometimes. We'll see what that looks like in the graph in a second. X-intercept, plugging in 0 for y, and I get 2. You can go to the margin and try that again, but we've been doing that for the past few days. Y-intercept, if I plug in 0 for x, I get 2 up top, but I get 0. So let me show you what happens here. If I plug in 0 for x, I get -2 up top, I get 0, and I get -5. Does that look weird to anybody? -2 divided by 0? Yeah, that's undefined, right? I mentioned this earlier. Because I have a vertical asymptote at x equals 0, that is the y-intercept, the y-axis. That means I'm not going to have a y-intercept. All right. Now, horizontal asymptote. Again, you can look at the top, the first function we had, or you can look at this reduced one. Be careful when you look at the reduced one. This is an x to the first in the numerator, but in the denominator you have an x to the first times x in the first. If you wrote this in standard form, you would have an x to the first over an x squared. So top degree is smaller than the bottom. That's a y equals 0 horizontal asymptote. All right. So that's everything pieced together, or every piece we need for the graph. Let's go ahead and start sketching a graph here. Vertical asymptotes at 0 and 5. So here's the vertical asymptote at 0. That's why there's no y-intercept. If you saw that right away, you could have saved time when we found the y-intercept. The horizontal asymptotes on the x-axis here. All right, so there's the setup. Now let's see what we have. We have an x-intercept at 2, 0. Now what the heck's going on there? We're hitting an asymptote. I know, that seems weird. So here's what's going on. And let's finish the points. Let's do some points and finish the graph, and then we'll talk about what's going on there. Don't freak out, that's okay. All right, so I've got everything pieced together. I think I need a few more points here to make sure I like what's going on. So I'm going to extend this. Now, here's what you got to realize. Remember, we always approach our asymptotes. So I need to find out what's going on here, what's going on here, and what's going on here. Basically, on both sides of your vertical asymptotes, you have to get points to see what's going on. So the first region I'm going to mess around with is over here, left of x equals 0, so negatives. So let's plug in -1. Okay? If I plug in -1, remember you're plugging into the reduced function here. One thing you might want to do, it's up to you, when it gets reduced, x minus 2 over x squared minus 5x. You could write it like that if that's easier for you to plug in numbers. I like plugging into the one I put a rectangle around, but either one will give you the correct answers. It doesn't matter. So let's see, if I plug in -1, I get -3 up top. I get -1, and then I get -6. So that turns into -3 over +6, which is -1/2, right? -3 up top, -1, and then -6. All right, so 1, -1/2. I come over here, sorry, -1, -1/2. So come to my graph, -1, -1/2. I've got a point down there. All right, so if you want to, on the fluency test, you can always plug in more points. I know what's going on here, and I know that first piece of the graph is down in this kind of left side corner here. So again, always approaching your asymptotes, right? So the first branch is looking like this. Approaching this asymptote, coming in, hitting our point, and then approaching this asymptote down there. Okay, so there's branch number 1. Again, I don't have to worry about a branch being up here because that's not going to happen. It wouldn't pass the vertical line test. Okay, now let's move over into the positives. Let's plug in +1, see what's going on. All right, so I plug in +1. Up top, I would get -1. I'd have a 1 out front, and I'd get a -4 in the parentheses. Again, plugging it in right there, plugging in 1 in for x. That gives me -1 over -4, which is +1/4. Okay? So plug in 1, I got a 4th. Let's plot that point. 1, 1/4, right there. Now I know what happens at 2. It's an x-intercept. Let's plug in 3. And again, there's no rule really about how many points you have to plug in. You've just got to plug in enough until you know for sure what's going on in that region of the graph. Right now, I'm not 100% sure what's going on. Right? I know there's 2 points kind of close to each other here. I want to find out what's going on over here, and then I have to go find out what's going on over here. So let's go plug in 3. If I plug in 3 up top, I get 1. On the bottom, I get, zoom in just a little bit here. I plug in 3, I get 1 up top, I get 3 out front, and then I get 3 minus 5, which is -2, so I get 1 over -6. So I plug in 3, I get -1/6. All right, that 1/6 looks weird. All right, so let's plot that point. 3, -1/6. So really close to the x-axis. All right, now here's what we know. That's maybe more than enough points, but that's okay. I want you guys to see a few more practice problems. I know those 3 points are all on this curve. Now, I know after this point here that the graph's not going to go back up. The reason I know that is because there aren't any more x-intercepts. Right? The only x-intercept was 2, 0. I know here, when it's coming in from that point, I know it can't do anything like this, right? A graph like that would approach the asymptote, but it wouldn't pass the vertical line test, right? So the only option in this middle piece is this thing's approaching that asymptote, it's coming down, it's hitting these 3 points here, and it's curving back down. This thing can't go over there like that and approach this asymptote because it wouldn't pass the vertical line test. So my only option, it's kind of making one of our x-cubed graphs, right? It's kind of making that snake shape in the middle. Okay. Now, I still know what you're thinking. How are you allowed to cross an asymptote? We'll talk about that in a second. Okay. Now, let's get another point. We have to go find out what's going on over here. All right. So let's plug in that vertical asymptote at 5. Let's plug in 6. Okay, so if I plug in 6, let's see what we get. I get 4 up top, I get a 6 out front, and I get 6 minus 5, which is 1, so I get 4/6, which reduces to 2/3. All right, is that right? 4, 6, yeah, 4/3. All right, or I'm sorry, 2/3. So let's graph that. 6, 2/3. 6 and 2/3 is right up here. All right, now listen, I could plug in more points, 7, I could 8, just to make sure they're all going to be above the x-axis. I know it's not going to cross the x-axis because, again, there's only one x-intercept right there, which is kind of another reason I knew this graph was done, or that piece of the graph was done, because I knew it was going to cross the x-axis again, I know it's not going to cross the vertical asymptote, so it's kind of stuck in that bottom left corner. I know this guy here is stuck in the top right corner. So sketch a quick graph here, make it curved, make sure it approaches your asymptotes, and your graph is done. Okay, so here's what's okay. I know it's weird. They are passing the horizontal asymptote, or crossing the horizontal asymptote. That is okay. Remember the definition of horizontal asymptote. It's end behavior. What happens as x approaches a big positive infinity or a big negative infinity. Okay? So way out here to the right, it's approaching y equals 0. Way out here to the left, it's approaching y equals 0. In the middle, it's okay sometimes. And in the middle, there technically isn't a middle. But sometimes close to where the asymptotes are, sometimes you will cross the horizontal asymptote. That's okay. So here's one thing you got to remember. Horizontal asymptotes, you can sometimes cross. Vertical asymptotes, though, you will never cross. Those are domain restrictions. Those are discontinuity values. You will never cross those. Okay? Horizontal asymptote, sometimes you'll cross. We're going to make it so that it's pretty obvious in the graph if it crosses the horizontal asymptote. Later on, you'll learn how to know whether to test whether or not it crosses. Okay? All right, last step, domain and range. Oh, now look, I made a mistake. Forgot my hole, right? So let's go back. Again, that happens sometimes. So if you're doing that, you're forgetting to graph the hole, I would do that right at the beginning, just so you don't make a mistake like I did. So -2, -2/7. See if I can squeeze that in here, -2, -2/7. Okay, so right about there. Again, it lines up on my graph, so you just remember to check it at the end. That's okay too. All right, -2, -2/7. Right there is my hole. And clean that up. All right, so there's my completed graph. Now, let's go back and do domain and range. Again, skipping over the hole. So, domain, I'm going to move this table over a little bit. All right, so the domain is negative infinity all the way up to the hole, which is -2. Then union, -2 to the vertical asymptote of 0, right? So negative infinity to -2, -2 to 0. Then I have 0 to 5, and then finally 5 to infinity. A lot of stuff to skip over there, right? A lot of domain restrictions. Now the range, this graph goes down forever, right? Because you have these two pieces here that go down. So negative infinity up to the y value of the hole, right? That y value was -2/7. So negative infinity up to -2/7. Union, -2/7 to the horizontal asymptote of 0, and then union 0 all the way up to infinity. And there is your domain and range. All right, so that's what the graphs are going to look like tonight. A little time consuming. I think we gave you 5 or 6 to work on. This should be over the next 2 days, not that much. Homework tonight, or today, you're going to do 2 things. There's a rational function feedback activity that's on Schoology. Now you can take that as many times as you want until you get 100%, so keep doing it. The order of the questions will be mixed up and the answers will be mixed up, so you got to know what you're doing. But if you don't get 100, take it again. Get that full credit. After that, there's a worksheet posted as well. That has a few practice graphs. So have a good day. Stop by the office hour if you get a chance and ask some questions. If not, shoot me an email. But office hours, we'll get a lot more done. Email takes me a little bit of time to get back to. So, all right, stay healthy, guys, and I'll